Thank you, Mark. Thank you for the invitation. It's a pleasure to be here. 35 years ago, I attended the conference for Thom's 65th birthday, I think, at IHP. And I remember Raoul Bott expressing his thanks to Thom for opening many doors in mathematics. And more importantly, he said, for opening some of them so little that he was leaving a lot of work for younger mathematicians. And in the case I want to explain in this talk, the doors were opened in Morse theory and differential inequalities, and the younger students who benefited from Thom's ideas were Smale and Gromov, so pretty smart people. Okay, so it's not just the centennial of Thom's birth, actually, it's also the centennial of Morse theory birth. So Morse theory started with the paper, this paper, Relations on the critical point of a real function of n independent variable, in which Marston Morse proves the so-called Morse inequalities for a Morse function on a compact domain in Rn, where you assume that the gradient vector field is pointing outward along the boundary. The paper was published in 25, but it was submitted in December 23. So most likely Morse was writing this paper right at the time of Thom's birth. So, as I said, in this paper, Morse proves the Morse inequalities, and so the focus is really on the filtration of the domain by the sublevel sets, or kind of alternatively, if you prefer, the partition of the manifold by the level sets. So, how does Morse... Do you have the slide, or by the way? Oh, I forgot, no? This slide. Oh. That's the first slide. Okay. Okay. Ah, no. Is that the second? Second. Second. Okay. Good. So, what is Morse's method to prove the inequality? The main result that you all know is the following theorem, that when you take two regular values, say A is strictly less than B, first, if there are no two regular values, if there are no critical values between these two, then the sublevel B retracts onto the sublevel A along the gradient trajectories. That's the first statement that everybody knows. And the second is that if there is a unique critical point whose values is between A and B, then, so Morse's statement at that time was just that the relative homology group of the sublevel B with respect to the sublevel A is 0 if the degree of the homology is different from the index, and is Z if the degree is exactly the index. And of course, nowadays, we no longer state this second result in this way. We say something like the sublevel B retracts onto the union of the sublevel A and a cell, a k-dimensional cell, if the index is k. But the main point why Morse could not prove such a thing is that he was working in Rn. So he was considering the Euclidean metric, and he was considering the gradient of the function for the Euclidean metric. But even if you use the Morse lemma to have nice coordinates near a critical point, the metric in these coordinates can be complicated, and so you don't control very well the gradient. And he was apparently not aware of the stable manifold theorem, for example. So he worked hard to control the behavior of the gradient near the critical point. And that's why he gets this result in homology. Okay, so now what about Thom's approach? Is that the right slide?
Yes. Yeah.
Okay, thank you. Thom, so the first mathematical research paper of Thom say is his note, whose title is on the cell partition associated with a function and a manifold. And in this paper, Thom associates to every Morse function what we can call a vertical partition of the manifold, which is a cell decomposition. And his approach is very different from that of Morse in the sense that the most striking feature of this note is that Thom completely ignores the level sets of the function. The focus is totally and uniquely on the gradient vector field. So let me explain in more detail what he does. The first thing is that he constructs a metric on the manifold, which near each critical point.
You should go to previous.
Oh, sorry.
Is that right? Which near each critical point is just the Euclidean metric in the Morse coordinates. So in these coordinates, the function is just given by a standard quadratic form. And so because of that, the gradient flow, since the metric is standard, is very easy to compute. And here you immediately see what is a stable manifold and what is an unstable manifold and all that. So that's the main trick he used somehow. And next, Thom observed that every trajectory of the gradient has to go from a critical point to another critical point, and that the set of points whose gradient trajectories converge to a given critical point is a cell whose dimension is exactly the index of the critical point. And so he exactly obtained his theorem that these cells, this what he calls critical cell, or let's say the cell descending from the critical points, form a partition of the manifold. So what is that good for? The next question. As Thom observes immediately, so I will translate in English, maybe in general, the so-defined cell decomposition of V is not the support of a cellular subdivision of V. However, it possesses some of its properties. Which properties? And what he claims, so for this, Thom gives neither example or explanations of what he just said, but he claims that you have the following consequences of his theorem. The first consequence is that the Betti number of, let's say, so what bk of vk is larger or equal to bk of v, and bk of vk plus 1 is equal to bk of v. What is vk? It's just the union of the cells of critical points of index at most k. And then the second claim is that the number of critical points of index k is larger or equal to bk, which is kind of what is known as the weak Morse inequalities. Okay. So does he prove that? Not really. And the reason is the following, that in the comments to this note, François Lodenbach gives an interesting example. So is that what you have on the slide? Is that okay? Do you have the example on the slide? Oh, sorry. Please complain. Is that? Oh, no. Why? Okay. Oh.
Voilà.
What is that?
Thom's approach. The first is first.
Next.
Par la decomposition.
Ah, okay. I'm very sorry. Okay. So just the manifold you consider is just S1 cross S2, and the Morse function you take is, let's say, the sum of what I write. Phi of x1 x2 is phi1 of x1 plus 1/2 of phi2 of x2, where phi k is just the standard Morse function on the sphere, which has a minimum ak at level 0 and a maximum zk at level 1. Okay? And so the critical points of this function phi are just as follows. You have one minimum, which is a1, a2. Next, you have, because of the 1/2 factor I've put, you have a critical point of index 2, which is a1, z2. Then, at level 1/2, then at level 1, you have an index 1 critical point, which is z1, a2. And at level 3/2, just a maximum. Okay. And the observation is that, so you see the critical point of index 1 is above the critical point of index 2. So if you slightly change the metric, you can arrange that one of the stable separatrices of the critical point of index 1 comes from the critical point of index 2. And because of that, the one cells, if you want, is just form a segment. And so the B1 of this one cell is 0, which is strictly less than the B1 of the manifold, which is 1. Okay? Is that clear? So something is wrong. And what you can observe is that the boundary of this V1 is not included in V0, which is the union of the 0 cells, because there is a unique 0 cells, which is the minimum. So what you define in this way precisely is not a CW complex. So do you see the Morse-Mill condition? Okay, so what's the remedy to this problem? The remedy to this problem is a Morse-Mill condition, which was, let's say, brought forth by Smale in his paper on gradient dynamical systems. And recall that the gradient field nabla phi is said to satisfy the Morse-Mill condition if every descending cell from a critical point is transverse to the ascending cells from the other critical points. And in that case, you have the following theorem, which has been, I think the first proof was given by Lodenbach in 92 and also approved by Latour 2 years later, which is that if this condition is satisfied, then Thom's partition is indeed defines a cell decomposition, a cellular structure, I mean a CW complex. So the key point in this result is that you implicitly assume what I call Thom's condition, which is that the metric is Euclidean, standard Euclidean metric in kind of Morse coordinate near each critical points. And this condition is also essential when you want to compactify the set of trajectories going from a critical point to another critical point. You can prove that there is a C1 compactification provided this condition used by Thom is satisfied. So, why does Thom, that's kind of question, why did Thom why did not Thom realize that this was the right condition to impose, right? And indeed, in his note from 49, he never mentions any transversality condition that you could achieve or that you have to assume to get a good structure. However, in 57, in his manuscript, where he gives a new proof of the Lefschetz hypersection theorem, Thom explains how to obtain the Morse-Mail condition that at the time was not yet called like this, of course. And let me show you what he says. We are back to the transparent about pluriharmonic function, I guess. So what he says is the following, that so he is considering a pluriharmonic function, Morse function, on a complex manifold, which is essentially the squared norm of a holomorphic function away from the zeros of the functions. So such a function has only critical points of index n. And Thoms writes the following, that he can make the descending cell disjoint. That's what he claims. And he explained, to show that the critical n cells are generically disjoint, we can argue sorry, just a minute. We can argue as follows. Suppose that a critical point Q belongs to the cell Z descending from a critical point P. So, of course, in particular, U of Q is strictly less than U of P. Then he says, in the level set U minus 1 of U of Q plus something, some positive number, then the set of points whose gradient trajectory lands on Q form a sphere of dimension n minus 1. And he says that the set of points that now descends from P form which can be a polyhedron, but also has dimension n minus 1. And because the level set has dimension 2n minus 1, he says that it's easy to change the metric so as to make them disjoint. So, which is exactly the argument Smale will give a few years later to show that his condition is generic. Okay. So let me come back to this paper I already mentioned about the proof of the Lefschetz. Is that the right? Morse theory in complex affine manifold? Okay. So in another manuscript, which is Homology of Stein manifolds, Thom extends his proof of the Lefschetz theorem to get a result which is a kind of confirmation of a conjecture of Jean-Pierre Serre, and which can be stated as follows, that when you have a Stein manifold, then its homology group in degree higher than the half of the complex dimension, in degrees higher than the complex dimension, so half of the real dimension, all vanish. And the Lefschetz hyperplane theorem can easily be deduced from this, just considering that the Stein manifold you are interested in is just the difference between the projective manifold and its hyperplane section. And, okay. What's Thom's proof of this theorem? Well, it works like this. The main point, the main observation of Thom is, again, that when you take the squared norm of a holomorphic function and a complex manifold, then away from the zeros of the holomorphic function, which of course is some complex subvariety of codimension 1, then the other critical points have necessarily, the squared norm is a pluriharmonic function, so its critical point of index n. And for example, how to use that? In the case of the Lefschetz theorem, so you can assume that your hyperplane section is at infinity. So what you are left with is an affine variety in C, let's say, to the D. And you just take a generic complex coordinate on CD. You restrict it to your affine manifold. And you take its norm squared, its squared norm. And so you get a function whose critical points, away from the zeros again, have index n. And that's how it does. But there is a difficulty here because this function is really non-proper in general. Or always, somehow. Because you have these zeros, for example, of the holomorphic function. You cannot get around this. So this makes his proof at some point technical. But two years later, Andreotti and Frankel just realized that the same kind of restrictions to the indices of critical points applies to plurisubharmonic functions. Their indices are bounded again by the complex dimension. And so instead of taking a coordinate on CD, you can just take the function norm of Z squared. And it works exactly the same. And it's much simpler because the function is proper. Merci, François. Okay, now a few words about what is called the Morse complex. So the Morse complex is a complex associated with a Morse function which computes the homology of the manifold. The first description you find in the literature is by Milner in his book on the H-cobordism theorem. And here is how Milner presents it. Assume that your gradient vector field is Morse-male. Then you can find the filtration of the manifold, start with empty set and ends with a whole manifold, where each domain Vk has smooth boundary transverse to the gradient. But it's not a sublevel set of the given function. It's actually the sublevel set. It consists of sublevel sets of a reordered function. But you have this filtration. And now with this filtration, Milner builds a complex which is the following. Ck, the K chain group is given by the homology of Vk relative to Vk minus 1. And the differential is just the connecting homomorphism in the homology exact sequence of the triple. So you see, here we are back to kind of somehow, of course, we use Thom's ideas, but we are somehow back to the point of view of Morse because you again consider sublevel sets. But in the 80s, Wien gave, in his famous paper, Supersymmetry and Morse Theory, he gave a presentation of the Morse complex which no longer uses any filtration, just the gradient flow. And the presentation is, as you know, that again, the chain groups are generated by the critical points, and the differential just counts with appropriate signs the connecting trajectories between the critical points. And really, this presentation is very much in line with what Thom was doing, and much closer to his kind of idea than the one of Milner. Okay, so just a quick thing that I will maybe let you read, just to say that I'm clearly not pretending that Thom invented things that he did not invent, and himself was not the kind of people to pretend he had done something he hadn't done. And I found very interesting what he said about Smale's work when Smale was awarded the Fields Medal, and he's very laudatory for Smale. Maybe let me read it quickly. The enormous merit of Smale in this question was that he dared undertake what any other mathematician of the time would have regarded as hopeless. And I think that when he said any other, he was thinking first of himself. And given a Morse function on a homotopy sphere, simplify the surge representation of this sphere by cancelling the exceeding pairs of critical points of index kk plus 1. That this was possible, we were too aware of the difficulties in low dimensions, 3 and 4, to hope for it. Smale dared and succeeded. Okay, so now quickly I would like to, not just to give a historical lecture, so I would maybe mention something which is related to Thom's work that I did a few years ago, which comes from the following, which is related to Thom's work in the following way. Of course, the works of Lefschetz and Thom on the topology of complex manifolds kind of raises the question of relating kind of more or less directly Picard-Lefschetz theorem with Morse theory. And let me recall that a Lefschetz vibration is the complex analog of a Morse function, but because the complement of critical values in the complex plane is connected now, you kind of perform, you want to have a map whose fibers are all the same. So somehow Lefschetz vibration is something which looks like a vibration, which is a vibration near infinity and whose critical points are non-degenerate. As Arnold used to say, when you realize that the Picard-Lefschetz is just the complexification of Morse theories, and this already invites you to think that, for example, pi1 is a complexification of pi0, And for example, Z2, which is or Z, which is a pi 1 of C star, is a complexification of Z2, which is a pi 0 of R star. And similarly, that monodromy is a complexification of surgery and so on. But what I would like to discuss is if we can find kind of direct relation between Morse theory and Picard-Lefschetz theory. And I will state it starting with a conjecture. Somehow I think...
Sorry. Is that okay? I will start with...
And what does the conjecture say? It says that, okay, just a minute. If you take a real analytic Morse function on a real analytic closed manifold, then I claim that there should exist a complex structure on the cotangent for which the function extends to a Lefschetz vibration, a holomorphic Lefschetz vibration, with exactly the same critical points. And okay, I still have a number of details to check in order to claim that I can prove this, but morally, it should follow from the next theorem and Eliasberg's work on Stein manifolds. And the symplectic version of the result is already proved, and the statement is the following, that if you take a Morse function now, smooth Morse function, a smooth closed manifold, then, and you assume, which is a necessary condition, by the way, you assume that the gradient is Morse-Smale. Then there exists a homotopically unique Lefschetz vibration on the cotangent, which takes the form H equals F plus Ij, where F plus Ig, where G is a very explicit function, just obtained by computing the covector on the gradient field. And the real part, F, is a function which, let's say, near infinity is homogeneous of degree 1 in each fiber. So I will briefly give the idea of the proof. Is that the...
Glimpse of the glimpse, but there are two glimpses.
The first one.
The small one. I hope it's glimpse number one.
So, what you first do is, on a small tube around the zero section in the cotangent, you can just take what I call first order complexification of the function, which is this complex valued function h of pq, which is phi of q, minus, say, the Hessian of the function of phi computed on pp, and you add this. I forgot to put some I before the g. Of course, it's the imaginary part, g of pq. Okay, you do that. And what you see very easily is that this map already has symplectic fibers. But of course, their topology is kind of varies. It's not the same, even for regular fibers. And basically because what can it be? It's essentially, let's say for real values, over a real value, any fiber is just a cotangent tube of the corresponding level set of the initial function. Just what you can expect. Now, you consider the restriction of this function, and in particular the real part, to the boundary of this cotangent tube, so to a sphere cotangent bundle. And what you see is that this restriction has more critical points. And indeed, the difference is the following, that over each critical point of the initial functions, you now have n critical points corresponding to the critical point you have generically for, well, by the way, or maybe I should say twice more, or, well, it doesn't matter, but I think it's twice more, because when you take a generic function, a generic quadratic form on a sphere in dimension n has 2n critical points, non-degenerate quadratic form, right? And so that's what's happening here. So I forgot this factor n, but it's better to forget about it. So, and the observation, so on each critical fiber, on each fiber over a critical point, you now have 2n critical points. And because the function is quite close, actually, to the initial function phi, because it's the boundary of a very small tube, then the function, the critical values are close to that of phi, and so the function is not ordered, as we say, which means that it does not satisfy the ordering condition that fr of Q1, P1 Q1 is less or equal to fr of P2 Q2 if the index of P1 Q1 is less or equal to, which implies, okay, that's written, to the indices, right? So what can we do? Because what we want is really to have symplectic fibers, but we want the fibers to all have the same topology. And what you just have to do is actually to reorder the function you have. So, but before that, you observe that this function you have, fr, is a Lyapunov function for the canonical contact lift of your vector field, the gradient on the base. So on the sphere cotangent bundle, you have a gradient vector field, which is just the lift of the gradient vector field, and your function is a Lyapunov function for this field. And now, because the gradient is Morse-male, actually this new bar, the lift is also Morse-male. It's easy to check. And so you can reorder the function to have the ordering condition I mentioned before. And once you have done that, so you have a family of function fr, for r very small, which leads to a function which is not ordered. And then for larger r's, you reorder the function, right? You get a family of functions. And if you take this family of functions to define the real part of your map, then once this is done, you get exactly all fibers now have the same topology. And you get the fibration. So that's the only idea I wanted to express. Okay, now something completely different, just to finish the talk. I wanted to discuss another paper of Thom, which is his paper entitled so as I say, maybe that's the most secret door that Thom somehow half opened. And so the title of the paper is Remarks on the Problems Involving Global Differential Inequalities. And what is that about? That's a paper in which Thom somehow starts the theory of open differential relation, which is a theory that Gromov will tremendously develop in the 60s and 70s. So a few observations before going into more details. First of all, nowadays, this theory is usually considered to originate in Smale's PhD thesis about immersions of spheres in Euclidean spaces, and in particular about the sphere eversion. And surprisingly, Thom, although he lectures on this work in the Bourbaki seminar in 58, does not mention it in his paper. I think that his primary goal is to ask questions and offer perspectives for future research. And the basic idea is that since you are considering an open conditions, which mean inequalities, you are requiring that you have a function with partial differential relations, partial differential derivative satisfy a system of strict inequalities. Because of this, you easily can find local solution. And so the main problems are about the global behavior of the solutions. And okay, what is the general type of problem you have? So consider, for example, two manifolds, V and W, and you take an open subset of the sets of R-jets of maps from V into W. And you say that a map from V to W is a solution of the partial differential inequality defined by your open set if its R-jet, JR or F, takes V into this open set. Okay? So again, think of this open set as giving inequalities that the partial derivatives of your function must satisfy. Now, if you have a submanifold, then by restriction you get an open set OS in the R-jet space of maps from S into W, defined by O. And the main question considered by Thom is, assume I have a solution of the restricted problem. Can I extend it to a global solution of O? And he distinguishes two important problems of that kind. What he calls Dirichlet type problems, which is the case when your manifold V is the ball and your submanifold is its boundary. And the second kind of problem that he calls Cauchy type problems, where the manifold V is a half space and the submanifold is its boundary, okay? And here, I would like to quote what he says, because I found these remarks quite interesting about the similarities between that kind of problems in PDEs and some problems in homotopy theory. We should note that these two typical problems that appeared in the theory of PDEs, the Dirichlet problem and the Cauchy problem, corresponds to two situations which are not less typical in topology. The extension of a map on the boundary of the ball over the ball, the whole ball, leads to the definition of homotopy groups. the picture of the Cauchy problem of the Cauchy problem is approximately the one which plays a fundamental role in the homotopy lifting property as well as in the Can axiom for semi-simplicial complexes. And I find this rather interesting. Okay. Now, what does Thom in this paper?
Did I go to the next slide? Or
Yes. Ah, non,
Non,
tu viens passer au suivant. Thom's approach.
Non.
Non, attends encore avant. Non, encore avant. Holonomy problème, c'est ça?
Oui.
So, what does Thom in this paper exactly? Well, of course, I should say that this pioneering work of Thom has been completely superseded by Gromov's work later. So, not everything is interesting in the paper, I would say, because the kind of point of view changed drastically. But still, I would just want to say a few things. For example, for the Dirichlet type problems, Thom defines homotopical and homological obstruction to the existence of global solutions. So it's the extension problem we are considering, which in the modern language are what we call obstruction to the existence of formal solutions. So he is aware of that, but he is mostly aware that the hardest problem in the theory is a so-called holonomy problem. And what is this problem? The problem is how to create a holonomic solution out of an arbitrary section of the jet space. A holonomic section out of an arbitrary section. Recall that the section is called, so a section G from the manifold V to the jet space is called holonomic if it has a form, if it is a R jet of some section from V, of some map from V to W. And how does he approach this problem? In the following way, that if you take, for example, the jet bundle for maps from Rn to Rm, then there is a canonical path systems which exactly measure the holonomy defect of sections. In other words, it is a system of path equation, one forms, which defines a plane field on your jet bundle in such a way that a holonomic section is exactly a section whose graph is tangent to this plane field. So a well-known and typical case is when you consider the one jet bundle of functions, so one jet bundle of maps from Rn to R. In that case, this plane field is just the canonical contact structure you have on the one jet space. And what does Thom prove? And I will finish with this, is the following theorem. That take an arbitrary open set in the R jet bundle and consider the inclusion of the complex of integral smooth singular simplices with values in your open set, the inclusion of this complex into the whole complex of smooth singular simplices. And Thom's theorem says that this inclusion induces an isomorphism on the homology group in degrees strictly less than n on a surjection in degree n. And so what's the idea of the proof? I will not go into any detail, but the idea is that what you need is a procedure to modify a simplex to an integral simplex. And for example, if you consider the case of one jet of maps from R to R, this procedure is well known in contact geometry. So you see, what is a one-jet space? You have three coordinates, x, y, p. And p is the derivative of y with respect to x. So you take a curve here, take a curve in 3 space, which is, let's say, given by a section, which projects kind of diffeomorphically to the first factor x. You take such a curve, and you project it in the xy plane. So you get a curve in the xy plane, which is not Legendrian at all. And you want to make it Legendrian. And so you know that your curve in 3 space, well, to be Legendrian, you need that the third coordinate be the derivative dy over dx. And so what you do, you have your curve in the plane, and you add many zigzags so that the slope agrees with the third coordinate which is given. And somehow, Thom's proof, I think, really is a generalization of this procedure. And I will stop here. Thank you.
Other questions? Now I have a remark that the unpublished papers have been published in Thom's complete work. Yeah.
Bon appétit.